Let's talk now about solving polynomial equations. So previously we were graphing polynomial functions. Solving them is a slightly different technique, and remember the goal of solving is always to find the roots. And I think I've emphasized this so far. We're finding the roots because then it's much easier to graph. We're going to start just by recapping what we had seen previously in grade 10 in terms of solving quadratics. That's like the basis, that's the most recent time you've ever seen quote-unquote solving. There were two methods of solving. The first one was factoring. The goal was to put it into a sort of a series of brackets and then make it equal to 0 on one side. Okay, so for example, x squared plus 8x plus 15, I'm going to factor that quadratic. So I'm looking for two numbers that add to 8 and multiply to 15. The answer is 3. So I'm going to, 3 and 5. 3 and 5. So I factor that and I include the equal to 0. That's like the most important part in solving. In order to solve, it has to be equal to 0. Next up, I need to solve for the variable by setting each individual factor equal to 0. Rearranging, I get x is -3 and x is -5. The other way that we solved quadratics was using the quadratic formula. Perhaps you remember this. X equals -b plus or minus square root b squared minus 4ac all over 2a. That was our quadratic formula. Again, in order to use the quadratic formula, we needed to make sure that all of the terms were on one side and the other side was equal to 0. Then we would substitute the values into the formula and simplify. And what I'm going to ask is that you don't use decimals, but you leave it as specific as possible. That includes leaving things underneath a radical and leaving things as a fraction. If from here you would need to graph, then absolutely you could calculate a decimal on your calculator in order to give you a good estimate of where to put it. But if you're just solving, the most accurate answer is the least simplified one. So let's do this example. 2x squared plus 4x minus 5. We substitute the values in. I have a, b, and c here. So x is equal to -4 plus or minus the square root of 4 squared minus 4 times 2 times -5 all over 2 times 2. And I continue. -4 plus or minus 4 squared is 16. -4 times 2 times -5 is 40. And it'll all be over 4. 16 plus 40 is 56. And we can simplify that radical. 56 is a product of 4 and 14. Plus or minus. And the square root of 4 is 2. So I'm going to do -4 plus or minus the square root of, 2 times the square root of 14, all divided by 4. If this step, going from root 56 to root 4, root 16, if that step is confusing for you, I need you to go on YouTube or go on Google and search for simplifying radicals. That's what you're looking for, okay? We're going to finish it off here. I can simplify this fraction. I can divide every term by 2. And that's as far as I can go. This is my most precise answer. The square root of 14 is going to give me a decimal, so I'm not going to simplify that, and therefore I'm not going to do anything with my fraction. And so my two answers for x are -2 plus root 14 over 2, and negative 2 minus root 14 over 2. Those are the simplest. Now, when we're solving polynomials, so higher degree polynomials, recall that there could be up to n roots. So there's a lot of different sort of options here. Let's do a quick one. I have a function x minus 3 squared, bracket x squared minus 10x plus 24. The very first step always is to set it equal to 0. And now I can take each individual factor and set it equal to 0. So my first factor is x minus 3. Squared. And my second factor is x squared minus 10x plus 24. I'll do the left one first because it's easier. I'm going to undo that square by taking the square root of 0, which is still just 0. And then rearranging to get x is equal to 3. That's nice and easy. The second one that I have is a quadratic here. I can see that I'm able to factor it using simple trinomial factoring, so I do not need to use the quadratic formula. This can be factored. I am looking again for two numbers that add to negative 10 and multiply to 24. Those two numbers are negative 6 and negative 4. And so from here, I can further break these down, and I can say, well, I can set x minus 6 is equal to 0, and x minus 4 is equal to 0, giving me x is 6 and x is 4. So I have 3 roots of this function here. 3, 4, and 6. That makes sense. This is a degree 4 polynomial. We have a 2 and a 2. The overall degree is 4. However, recall with your polynomial sketching that this root, what's actually happening is it is approaching the x-axis and it's rebounding off of it. So we're only hitting it at that vertex. So it makes sense that there's only 3. One where it rebounds, and then the other 2, they must cross normally. Now, when you're faced with polynomials that are expanded, so they're not previously factored for you, you need to factor them, okay? And the line that I'm going to highlight for you here is the really most important bit is I want you to try all different types of factoring before you use factor theorem. Factor theorem is a slow method because it requires you to guess and check. If you're able to factor another way, I guarantee you it is going to be faster, and part of mathematics is efficiency. Let's look at this one here. This is a degree 3 polynomial, which indicates to me that I cannot factor it using the regular quadratic factoring. The degree is too high. I could jump straight to factor theorem. Yeah, that would work. But I recognize on first glance here, I can take a look and say, well, what if I factored by grouping? It looks like I could. The first two terms have a lot in common. The second two terms have a lot in common. Let's see if this is going to work out. So that's what I'm going to do. I'm actually going to group these, and I'm going to factor by grouping. Okay, I'm just going to rewrite that equation. My first group is going to be x cubed minus x squared. And my second group is going to be negative 9x plus 9. Out of my first group, I can factor out an x squared, leaving me with an x minus 1. And out of my second group, I'm going to factor out a negative 9, leaving me with x minus 1. Factoring by grouping worked here, which is amazing. I'll continue it off. I now have an x squared minus 9 times x minus 1. So the first thing I did here, I factored by grouping. Now we're at a point where I'm like, okay, I could call it, but are there any other factoring methods that I can use? And then there are. Our x squared minus 9 is a difference of squares. So I'm going to factor that guy using difference of squares. The square root of 9 is 3. I'll have one bracket with a plus, one bracket with a minus, and can't forget that x minus 1 from before equal to 0. This is the most factored form of this equation, therefore we can go ahead and set all the factors equal to 0. And solve. X will be equal to -3, +3, and 1. And we can write a concluding statement to that effect. Doesn't really matter what order you write them in. Okay, so this is a question we were able to avoid factor theorem in order to solve. Now this one. This is going to get really interesting, okay? We cannot use quadratic factoring methods. We cannot factor by grouping because there's an uneven number of terms, there's an odd number of terms. Can't do that, so we're stuck. In this situation, I'm going to revert back to factor theorem and just going to factor it out that way, see if I can simplify and at least reduce the degree on this polynomial to sort of help ourselves out. So factor theorem, I need to find my possible p-values coming from the 20. So that'll be 1, 2, 4, 5, 10, and 20. All of them being plus minus. Okay, I set my equation equal to f of x. And I'm going to check 1. Recall that all that means is I'm substituting in 1 for all of my values, and let's solve. 1 plus 4 minus 9 minus 16 plus 20. Let's see. This is 5. Take away 9 is -4. Take away 16 is -20. Plus 20 is 0. Yay! X minus 1 is a factor. Let's factor this now using synthetic division. I write my coefficients. And we go. Bring down the 1, multiply across. Add down, multiply across. Add down, multiply across. Add down, multiply across. Add down. We did it. We have a 0 at the end. So the factored form that we're working now with is going to be x minus 1, x cubed, plus 5x squared, minus 4x, minus 20. So we found one of our factors. Now we can take a look and see, okay, can I factor this any other way? It looks to me like we should be able to factor by grouping. So that's what I'm going to do for my quotient here. I'm going to factor by grouping. So I'll take my, you know what, I'll do this all in one line. My first group is going to be x cubed plus 5x squared. From there, I can take out an x squared, leaving me with an x plus 5. And then in my second group, I'm going to take out a -4, leaving me with an x plus 5. Continue the factoring by grouping, and I have an x squared minus 4, and then an x plus 5. Awesome. And now it looks like I can also factor my x squared minus 4 as a difference of squares. That difference of squares is going to be x plus 2, x minus 2, and then entirely we add the x plus 5 at the end there. So this is my most factored form. I cannot factor any further, which is perfect. That's what I want. Now I need to set all of the individual factors equal to 0. X will be 1, negative 2, positive 2, and negative 5. So already concluding sentence. Just to be fancy, I'm going to write them in ascending order. Okay? Not that bad at the end of the day. It just takes time to find the solutions. We've confirmed that these are our roots now, and we could go ahead and factor it if we wanted to. Okay? That's it. That's all you need to know about solving polynomial equations.